Hello everyone. In this video, we will learn about an important implication of two events being independent. Well, recall that two events E and F from the same sample space are called independent events if knowing that one happened doesn't change the probability of the other ones. In other words, if I calculate probability of E knowing F and I calculate probability of E without knowing if happened or not, these two things must be equal. So that is the definition there. But you said, okay, the left-hand side here, I can write it in terms of intersection, probability of intersection divided by probability of the given part. And well, that is just equivalence there. Well, there's a small condition that F probability of F must be non-zero, but at the end turns out that the final thing that I multiply this to the other side will always be true. When E and F are independent, then probability of E and F can be calculated by product of probability of E and F. Probability of E and probability of F. So you see, this in general is not true. Only if E and F are independent. And since I'm putting this one here, it means that it is equivalent. It means that the right-hand side, if you have two events that for which the right-hand side occurs and satisfied, the right-hand side is satisfied, then E and F are independent. So here, then let me put them down as remark. So the first remark is that when E and F are independent, only then we can use the right hand side, the star, to calculate probability of the intersection. And the second thing is the reverse of this. Star can be used to determine if two events are independent or not. Well, you may say that, okay, I already had a definition for that. I could go and do the conditional probability, but conditional probability sometimes is not easy or sometimes are not available. Probability of intersection and probability of each one is more often you can find in the question. So that means that, yes, that star gives you two-folded tool. That one, you can use that to find intersection. The other one is that use it to check if two events are independent or not. Let's see this in an example, or maybe two examples. Here E and F are given. Probability of E is 0.2, probability of F is 0.5. Then we are looking for probability of union. Well, you know that when you have probability of E, F, and union, what you can looking for union, you cannot just find it by knowing probability of E and F, because the formula which gives you the union also includes that minus E intersect F. And in general, if someone gives you probability of E and F, well, there's no way you can find probability of union of these guys. But in this case, E and F are independent. that means that I can use the fact that probability of the intersection for independent guys is going to be product of probabilities of these events, and in this case is 0.2 times 0.5, which is 0.1. So knowing that E and F are independent, I was able to find probability of the intersection. Now I can take that, put it in that inclusion exclusion formula. Let me write it down here and calculate what is probability of union. So this is 0.2 plus 0.5 minus 0.1, the intersection, that will give me 0.7 minus 0.1, which is 0.6. Part 2 or part B says find probability of E knowing F. Well, you should remember that E and F are independent. Yes. And by definition, it means that knowing F already happened won't change probability of E. So the condition of probability E given F is going to be equal to probability of E, and in this case it is 0.2. Well, you may say that, no, I want to use the formula since I have the probability of intersection in hand. Why don't I use the formula? Well, you go ahead, you can definitely. Well, just to let you know that you're going around yourself and you're doing something extra work there, but well, it's a good thing to check. Probability of intersection is 0.1, probability of E is 0. Sorry, I should put probability of F in the denominator. That's 0.5. This is 1 over 2, which is same thing as 0.2. Yeah. Well, let's do another example. Here, three cards are drawn from a deck of cards. Let B to be exactly one. One black is drawn. H is exactly one. A heart. Then we want to check if these two are independent or not. So we can use that star. Remember, if we know what is the probability of intersection and we know probability of each one, we will try to see if product of the probability of each one is equal to probability of intersection. So I'll go with this first. Probability of, basically I'm looking for exactly one black and not black and one heart. Well, remember there are 26 black cards, spade and club. So I want to choose one out of these guys. Then I want to choose one from the heart. So this is heart. These are blacks. But I still need to choose one more because we are taking out 3 cards, yes? So the rest will come from diamonds. And well, then the total number, or N of S, is 52. Choose 3. Well, you'll need to do some calculation here. I have already done, and I know that the numerator is 13 times 13. The denominator is 2 times 17 times 25. So that's probability of intersection. How about probability of B, exactly one black? This is, well, first of all, we are choosing 52, 3. Exactly one black means that 26, you choose one of them. And then, so these are the black ones. Then the rest should come from the red ones. In other words, heart and diamond together. There are 26 of them, and I want to choose 2 from 26. And if I simplify this once, I will get this number that 13 divided by 2 times 70. How about probability of H, which is probability of exactly 1 heart. This is, okay, 13 hearts, choose one of that. The rest will come from the black ones and diamonds. And if you do simplify this, you will get to this number, which I will try to write it as simple as we can. Well, this is not maybe simple, but the point now is that is probability of the intersection BH equal to probability of B times the probability of H. So on the right hand side we have 13 over 2 times 17. You multiply this by 3 times 13 times 19, 4 times 17 times 25. On the left hand side we have 13 times 13, 13 times 13 divided by 2 times 17 times 25. But you see, if you set these two equal to each other, you notice that yes, okay, I have 125 here, will go with that 25. There's 117 will go with that. There's 2 will go with that. There's no denominator on the right hand side. Okay, so I can do 13s as well. But what will stay here that we are trying to see if 1 is equal to 3 times 19 divided by 4 times 17, which is obviously not equal, not equal, not equal. As a result, B and H are dependent events. And there we go. So we use that formula to check if these two guys are independent or not. The answer was they're not independent. They are dependent events.